Okay, well, after the two introductory talks, we now move on to introduction to molecular semiconductors, which is obviously a Cambridge interest. And I'll introduce my colleague Henning Sirringhaus, who's going to talk about transient localization.
Thank you, Richard. It's a great pleasure for me to have the chance to talk to you about organic semiconductors. And what I would like to do is to speak about how we think about wave function localization in these systems and what the origins of wave function localization in these systems are. I'm an experimentalist, so I'll not be able to cover some of the more theoretical frameworks in which we do this, but I'll try to give you an experimentalist perspective on this question. And then later in the afternoon, Jochen Blumberger will talk a bit more about the theory, how we can understand this theoretically. But let me start by introducing what an organic semiconductor is. So if you remember from your undergraduate chemistry, benzene is this planar hexagonal molecule, which is essentially made out of 6 carbon atoms. Carbon has 4 valence electrons, and three of these 4 valence electrons basically form covalent bonds in the plane of this molecule to 2 neighboring carbon atoms and to a hydrogen atom, which is not shown on this diagram. But then you have a 4th valence electron left, which is in a pz orbital, which is sticking out, a p orbital, which is sticking out of the plane of the molecule. And with these pz orbitals, you can form coherent superpositions, electronic states that are essentially delocalized over this molecule. And the lowest energy state is a state that has essentially no nodes, where you form a coherent superposition of these 6 carbon pz orbitals, and then you can incorporate 1 node, 2 nodes, and so on. You can make higher lying molecular orbitals. And then you fill these molecular orbitals with the 6 electrons that you have, from each carbon atom 1, and then you have a highest occupied molecular orbital, and the next one up that remains unoccupied is the lowest unoccupied molecular orbital. And these 2 orbitals, they basically form what you might call a valence band and a conduction band in a conventional semiconductor, which Claude has just introduced. And so the HOMO, the highest occupied molecular orbit, is the kind of equivalent of the valence band, is completely filled, and the LUMO, the lowest unoccupied molecular orbit, is the equivalent of the conduction. And then what an organic semiconductor, of course, can be much more complicated. You can line up these benzene rings. You can ask an organic chemist to line up these benzene rings along a linear chain, for example, to make a polymer. But the electronic structure of these systems is quite similar. You can form delocalized molecular orbitals along the chain of the polymer or along a molecule, extended molecule. And the main thing you do is you tweak the band gap between the occupied and the unoccupied levels. It's a field that's to some extent driven by chemistry, because organic chemists are very clever and they can make beautiful molecular structures, not just containing carbon, but they can incorporate heteroatoms, sulfur and nitrogen, and you can make complicated geometrical structures, and with that we can tune the electronic properties, we can tune the band gap, we can tune the charge transport properties. And so what we physicists here in the Cavendish do, we try to understand some of the structure-property relationships. How does molecular structure relate to physical properties, optoelectronic properties, charge transport properties? We like to make devices, so there is a number of applications for these organic semiconductors that you might be familiar with. Many of you will have an OLED phone, a phone with an organic LED screen. So this is essentially a technology where you use an organic molecule as the light-emitting element in a light-emitting diode, just like the indium gallium nitride LEDs that Claude has introduced. The organic semiconductors also make very good LEDs, so that's one of the main applications. But you can make solar cells, you can make electronics. I don't really want to talk about the applications, but just to provide the context. There are two classes of organic semiconductors that we are interested in. The first one you can see on the top here, that's what we call a small molecule organic semiconductor. So here you have a kind of a core conjugated unit, these four rings here that are fused together in this way. We often have what we call side chains attached to these molecular cores. These side chains are simple alkyl chains, so CnH2n+1 units. They are not electrically active. They are not conjugated in the same way as I've described for the core, but they provide some of the solution processability. They are more flexible chains, and they allow us to dissolve these molecules in an organic solvent, and that allows us to coat them on a substrate in order to make samples, in order to make films, or also grow crystals of these materials. And the nice thing about these molecular systems, these small conjugated molecules, is that you can crystallize them. You can grow, in principle, you can grow perfect single crystals. And here you can see the crystal structure of one of these molecular semiconductors, where you see that the conjugated units of neighboring molecules, they like to pack together in layers. And these flexible side chains, these alkyl side chains, they stack also in layers. So you have a kind of like a super lattice. You have a two-dimensional layer of conjugated molecules, and then another layer of alkyl side chains, another conjugated layer, and so on. That's how the single crystals look like. And within these conjugated layers, you have essentially a close packing of these molecules. They are not covalently bonded because there are no covalent bonds formed between the molecules. It's a weak van der Waals interaction that holds the crystals together. And within these two-dimensional conjugated plates, you typically have what we call a herringbone packing, where essentially the face of one molecule faces the edge of the neighboring one. That's how they like to pack. And in these molecular systems, that's the simplest organic semiconductor, where it's easiest to understand the transport physics, and you can get relatively high carrier mobilities. It's on the order, I mean, we measure the carrier mobilities in units of centimeters squared per volt second, and you get values of maybe 10, 15. It's about 10 times lower than silicon, and that's because we're not forming really strongly interacting molecular. We don't have strongly interacting molecular units, but they're relatively far apart. They're not interacting strongly, but you can achieve quite sizable carrier mobilities. On the bottom, you can see the second class of organic semiconductor that I want to talk about, and that's what we call conjugated polymers. And so here we have not a small conjugated unit, but a long extended chain, a polymer chain. Chemists can also synthesize these very well. These typically don't crystallize so well because they're too long and their length is not so well defined. The chemists are unfortunately not perfect. They make them with maybe 100 units and 101 units or 102, and that prevents these polymers from forming single crystals. So you tend to have more like a bowl of spaghetti in a sense. So these chains are disordered, they are running in random directions, and it's a much more disordered system. And so I want to describe in this talk the basic transport physics, how we think about transport in these two classes of semiconductors. Let me start with the molecular system, the crystalline, the single crystals. And if you are a solid-state physicist and think about this problem, you would say, okay, we have a molecular crystal. Here you can see a projection of this herringbone stacking that I described. You're looking at the molecule along its long molecular axis. You can see this face-to-edge characteristic packing for this molecule here, which we call pentacene, these 5 fused benzene rings. But it is a single crystal, and you can let band structure calculations loose on this single crystal. So what you would in principle expect is that you can form extended Bloch electron orbitals, as we have already heard. There should be no disorder in a perfect single crystal, you might think. So you should be able to form Bloch electrons. And if you ask a theoretical physicist to calculate the band structure of such a molecular crystal, what he or she will come back with is a band structure that looks a bit like this. And those of you who have seen band structures before will notice that the bands are very flat. They essentially look like uncooked spaghetti. And that's because it's the interaction between the individual molecules is not so strong. If you did this for a silicon, you would see bands that are basically fluctuating wildly as you go across the Brillouin zone. But in these molecular systems, the bands are flatter, and that's because the electronic interaction between neighboring molecules is not so strong. And that is because the molecules don't get very close. They are typically 3 to 4 angstroms apart in these crystals, and as a result, the transfer integrals, the integrals that determine the interaction between neighboring molecules, tend to be only on the order of 100 millielectron volts, rather than being on the order of a few electron volts, as you would have it in silicon. And so that's one of the characteristic features of organic semiconductors, and let's have a look at what some of the manifestations of this are. So I show you here some characteristic transport signatures in these molecular crystals. What you see on the top left is the temperature dependence of the mobility in one of the most commonly studied systems. This is called rubrene. It's a particular molecular semiconductor where you can grow beautiful crystals. And what you see here is that at room temperature, the mobility is on the order of 10. And then as you go towards lower temperature, the mobility increases a little bit. Around 200 Kelvin, you reach slightly higher values. And then as you go even lower, the mobility plummets. And that's due to some residual disorder, which I don't want to discuss now. Basically up to 200 Kelvin, down to 200 Kelvin, you see pretty much the intrinsic charge transport properties of the single crystal in the absence of disorder. And this is the behavior that you might see in silicon. If you measure the mobility of silicon, you would see something very similar. As you cool down, the mobility increases. And that's because electrons that are in these extended Bloch electron states, they scatter less and less with phonons. As you cool down, there are fewer and fewer phonons, and the mobility becomes larger because there is less effective phonon scattering. On the middle, in the bottom here, in the middle, you see what we call the Hall effect. So essentially, if you put a system like this into a magnetic field, apply a magnetic field and measure the transverse Hall voltage, you see a very well-developed Hall effect. And we take the Hall effect as a kind of experimental probe of coherence in a system like this. If you had a system where you have localized electron states, where the electrons are hopping from one side to the next, in a disordered system where all the states are localized, electrons are hopping from side to side, you would not see a Hall effect. We tend not to see a Hall effect. But in a system where you have Bloch electron states, you would see a well-developed Hall effect. And so in these crystals, you can see a well-developed Hall effect. But there are a few signatures in these molecular systems that are puzzling. On the top right, you see the optical conductivity measured at low frequencies. And if you had a perfect Bloch electron system, you would see a Drude, what we call a Drude optical conductivity, where the optical conductivity basically rises towards zero frequencies. But in these molecular systems, we see just before you come to zero frequency, at very low frequency, we see a drop of the optical conductivity, and that's not expected for a free of Bloch electron system. So this is turns out to be a signature of localization. We see similar things if we do optical spectroscopy on the carriers. So this is an experiment that we are very fond of here in Cambridge, where basically we make a transistor structure, so where we have a gate electrode, essentially to control the number of carriers in the semiconductor. When you apply a gate voltage, you can induce carriers electrically in the semiconductor. And then you can put this device into an optical spectroscopy setup and measure in a sense, the optical absorption spectrum of the charges that you induce in the material. So in a molecular system, the neutral molecule has a characteristic absorption signature, just like Claude explained for indium gallium nitride. You basically promote electrons from the occupied molecular orbit, occupied HOMO level to the unoccupied LUMO level, and that gives rise to optical absorption. But if the molecule is charged, you're essentially doing this optical absorption experiment on a different molecule, because it's not an n-electron system, but an n-1 electron system, and you would expect to see a different optical signature when the molecule is charged. So it's a specific of molecular systems, because it's small electron numbers. When you charge the molecule, you observe a slight shift in the optical absorption. And that's what we can measure in these experiments. And what's peculiar about it is that when we do these experiments on a solid-state system, where you might expect the electron states, if there were Bloch electrons, we should not really see very molecular signatures in these absorption features. But what we do see, you can see that here. So what we see, but basically when you induce a charge on a molecule, you bleach the neutral absorption of the molecule, and instead you generate these very characteristic charge-induced absorptions at kind of frequencies in the at lower frequencies. And what's important here is that these charge-induced absorptions that we see in the solid state, they basically look very similar to the absorptions that you would see if you doped a molecule in solution. If you basically take one of these molecules, dissolve it in a solvent, so that it's in an isolated environment, it's just a single molecule in solution, and you chemically dope it, induce a charge on that molecule, and you measure the absorption spectrum of that. That absorption spectrum looks very similar, you can see that here, to compare the red and the blue curve here, to what we would see for a charge carrier that carries a current in an FET. And what that tells you is that the wave function of these charges must be not very different from the wave function of the charge on an isolated molecule. Because otherwise, in solution, the charges have to be confined to the individual molecules, and if the charges in the solid state optically look very similar to the charges in an isolated molecule in solution, that tells you that the wave function can actually not be a fully extended Bloch electron, but it must be more localized. And we've tried to quantify this. I don't really have time to discuss this. We have tried to work with theoreticians like David to basically understand how we can model these charge-induced absorption. And the result of that is that essentially the charge carriers in these molecular crystals are not fully extended Bloch electrons, but the wave function is localized on small molecular clusters. We would love to know how large these clusters are, whether they are the wave function is localized over 10 molecules or 5 or whatever. We currently don't have a very good experimental probe to measure this, but the evidence is very clear that we're not talking about Bloch electrons here, but we're talking about electrons that are somewhat delocalized, but only over a small molecular cluster. And so what's the physics that's responsible for this? And so I've already mentioned that one of the characteristic features of these molecular systems is that they are not covalently bonded, but they are only weakly van der Waals bonded in the solid state. And one consequence of that is, so if you think about two molecules in the solid state, they are not really strongly interacting with each other. So that means that you can have very significant thermal fluctuations in the lattice positions. So the bad news here is that unfortunately the molecules are not static, they are moving. And at room temperature you have relatively large thermal fluctuations of the position of neighboring molecules with respect to each other. You can see that directly if you, for example, do transmission electron diffraction experiments. So this is a TEM diffraction pattern of this molecule here, which we call TIPS pentacene. And you can see these very sharp diffraction spots
and they basically tell you about the molecular crystal structure. You can work out the crystal packing from these sharp diffraction spots. But then you can also see these diffuse streaks in the diffraction pattern. And these diffuse streaks are unusual. And we were able to show a few years ago that they are essentially manifestations of these relatively large thermal lattice fluctuations. So at room temperature, the molecules are moving all the time with respect to each other. And we developed a model, a model to analyze these diffuse streaks, and were able to extract the amplitude of these thermal lattice fluctuations. And what you can see here is that at room temperature in this molecule, the thermal lattice fluctuations have an amplitude of about 0.1 to 0.2 angstroms. So one molecule with respect to the neighboring one, they fluctuate with an amplitude of a few tenths of an angstrom. And so now you can ask yourself, is that relevant? Do I need to worry about this? And the answer is yes, you should worry about it. Because if you ask yourself how sensitive might the transfer integral be to these thermal fluctuations, you can ask again a theoretical chemist or theoretical physicist to calculate the transfer integral between two neighboring molecules as a function of the relative position between molecules. And so here you can see how the transfer integral between two of these molecules varies as you slide them along their long molecular axis. So for different positions, you calculate the transfer integral, and you see here that there are some positions where the transfer integral is large and positive. You have some positions where the transfer integral is 0, and some positions where it's negative. So it oscillates as a function of the long axis displacement. And the origin of that is very simply that, of course, the wave function of these, in the HOMO and LUMO wave functions, they have lobes that are associated with these carbon pz orbitals. And as you slide the molecules alongside each other, the overlap between these lobes changes, and as a result, the transfer integral changes. So if you now think about how that affects the transport properties, if your equilibrium position is somewhere here, and now these molecules fluctuate against each other, this essentially means that a charge sitting on one molecule will see a temporally fluctuating network of transfer integrals. The transfer integrals to the neighboring molecules, they are varying on a picosecond timescale on which these vibrations occur. So the charges are moving in a dynamically disordered environment where the transfer integral between molecules are changing on a picosecond timescale. The lattice is perfectly single crystal. I mean, there's no defect. I mean, there are some defects, but we're pretty sure that we don't need to worry about them, at least near room temperature. But the landscape in which the charges are moving is dynamically disordered. And so how do we understand transport in such a system? And this is where this theory of transient localization comes in. It was developed by Alessandro Troisi and Simone Frattini, this is a cartoon that basically illustrates the concept. So essentially these dynamic fluctuations of the transfer integral, they prevent the electrons from forming macroscopically extended Bloch states, but they localize the charges. So the wave function here at this particular point in time, the wave function is localized over these 5 molecules. It's prevented from further delocalizing by molecules that are kind of configurations that have small transfer integrals and that prevent then the wave function to delocalize further. But it's a dynamic process. A picosecond or so later, maybe the electron wave function is localized over here, over these 7 molecules. Another picosecond later, it's over here. So the way we understand transport is essentially that the electron wave function is surfing on the waves of molecular lattice distortion. As the molecular lattice evolves, the electron wave function is kind of pushed through the molecular lattice. And that process is a diffusive process, and this diffusive process governs the mobility. So the mobility of charges in a system like this is governed by 2 key quantities. One is the delocalization length L, which is essentially the length scale over which the electron wave function is able to delocalize. The longer this delocalization length L is, the better. And then the second key quantity is the vibration frequency, omega naught. So what this equation says is essentially that the diffusive process occurs by every time the molecular lattice evolves, the wave function moves by a length scale L. So what we want for high mobility systems is a long delocalization length and stiff molecular lattices with large vibration frequencies. It's actually a little bit more complicated. I don't want to give you the impression that this is all very simple, so let me just talk for a few minutes about some of the complications. And one of the complications comes from the fact that we're talking about very complicated systems. The unit cell of a molecule like this has maybe 100 atoms in the unit cell, and that means you have, if you remember your solid state physics courses, there must be about 300 phonon modes. So which of these vibrational modes are actually responsible for this disorder? Is it everyone that we need to worry about, or are there specific modes that are very effective in generating this dynamic disorder? And so we've studied this question using a low frequency spectroscopy. We're mainly concerned here about phonon modes that involve intermolecular motions, relative motions between molecules. And with the combination of these two techniques, terahertz optical spectroscopy and neutron scattering, you can basically analyze these phonon modes. So what you see here is essentially a plot of absorption, optical absorption and neutron scattering as a function of energy. On the left is the terahertz spectroscopy, where you basically get down to very low frequencies, where you measure the softest modes, and then you go up to higher frequencies, where you move towards the stiffer intramolecular modes. So essentially each peak here corresponds to a particular phonon mode, a particular vibrational mode. And we are able to simulate these spectra. We're using a high-level DFT. We can reproduce these spectra quite well. For some molecules, we almost get perfect agreement between the DFT simulations and the experiment. The experiment is in solid line here, and the theory is in dashed line. And so we know what each of these peaks, what phonon mode corresponds to each of these peaks, and what the energy of that mode is. And then we can analyze basically mode by mode the electron-phonon coupling. So the DFT tells us what the normal mode coordinate is. We know how the molecules are moving with respect to each other for that particular mode. We can then calculate the electron-phonon coupling, which is essentially, the electron-phonon coupling is a measure of how strongly such a vibrational mode with this particular pattern, for example, how strongly that modulates the transfer integrals. Yeah? Depending on what the mode pattern is, the modulation of the transfer integrals will be different. There might be some modes that modulate transfer integrals very strongly, and some modes that don't affect the transfer integrals very much. And so we can analyze that mode by mode, and then basically calculate the resulting disorder. Adding it all up, each mode contributes a little bit of disorder, and you add that up, and you end up with a plot that basically measures, the sigma measures the total thermal disorder in the transfer integrals that's generated by these individual modes. And the red line is a cumulative plot where you can see how it builds up as you go mode by mode from low frequency to high frequency. Yeah? And what's quite interesting is that actually, if you look at this molecule here, this particular molecule, you can see that as you build up this disorder, a lot of the disorder is built up by one single mode. There's one big step in this curve here. This lowest mode, this blue mode here, generates 70% of the thermal disorder. And all the other 299 modes or whatever generate just a little bit more. So that's quite interesting from a molecular design perspective, because it allows us to then target these individual modes, because what we want to do, of course, is to suppress the electron-phonon coupling, allowing the charges to be more delocalized. And so we now know which modes we need to target in order to achieve that. And then we have a model that Jochen is going to talk about more in detail, which allows us to calculate mobilities. So using this expression here. I don't really, probably don't want to go into very much detail, but what you can see here is the correlation between the experimentally observed mobility in a single crystal and the theoretically predicted one. And within this transient localization framework, we can get a reasonable correlation between experiment and theory. So the materials that are predicted to have the highest mobility, they actually also show the highest mobility in the experiment. It's not perfect, there are some surprises, but this transient localization framework seems to give a very good description of the kind of structure-property relationships that you would expect. So it's becoming, in the last couple of years, it has become, I guess, an accepted framework for understanding these molecular systems. So with that, I want to quickly conclude what I have told you about molecular systems. So this transient localization framework, I think, explains some of the key aspects of the transport physics of these molecular systems. And we're getting to a point where we can have a very detailed understanding of how the individual phonon modes basically generate this thermal disorder. In the second part of the talk, I now, maybe more briefly now, talk about conjugated polymers. So this is a more complicated situation because we don't have single crystals. We have very messy spaghetti type systems. So this is a cartoon here that kind of illustrates how we think about the network of a conjugated polymer, where these individual lines here symbolize the conjugated chains. And then you have maybe small regions, these orange regions, in which maybe the chains aggregate somewhat, maybe form a small crystalline domain. But in between, you would always have more amorphous regions where the polymer is more structurally disordered. So in a system like this, if you think about the individual conjugation segments of the polymer, so if a charge sits somewhere over here, it will be in a particular intermolecular environment, and we'll see a kind of different kind of chains next to it. And if it sits over here, that environment will be completely different. So, and as a result, we'll have what we call static disorder. This is a static landscape of energetic disorder. Just like Claude described it for indium gallium nitride, in this case, the variations, the local variations of the molecular conformation and the intermolecular environment, they will cause fluctuations or variations in the energy of the HOMO and the LUMO levels. And then we think about transport in these systems basically as a hopping transport in between these molecular sites. And they differ in energy. They also differ in the delocalization of the wave function. I mean, there are some states, typically what you see here in this, it's a little bit a complicated diagram, but maybe I take the time to explain it. So the x-axis here is a lateral position where basically you have, as you go in a particular direction, you see the states that exist in the conduction band at this position. The y-axis is energy. So the states here at low energies, they are the states that are close to the conduction band edge, and the state that are at higher energy, they are in the conduction band itself. So here would be the tail states in the density of states, and as we move up, we would move towards the band of states. Each state is represented here with a line, and the longer the line is, the basically longer the delocalization is. So the states that are close to the band edge, they don't have lines, they're basically dots, and what that means is that they're more localized. And then as you go higher up into the band, you have more delocalized states, just as it was described by you in the first talk. So the delocalization changes as a function of energy. And when we're thinking about transport, we need to now worry about how do charges, that's a charge that sits here, hops onto a higher lying energy state and moves through that network of sites. And what's quite interesting is that in systems where you have such delocalized states at higher energy, actually they become very important in the transport properties because they allow longer range hops. So with these delocalized states, you can hop over longer distances. You have to expend some thermal energy, but you allow longer range hops. And a question that I now want to discuss a little bit in detail is how the vibrational dynamics is important in this. If you take the view that, we have a static disorder landscape, you diagonalize your Hamiltonian, you get eigenstates within that landscape, but they're not coupled. So what causes the coupling? The coupling is caused by the vibrations. Yeah? So the structural, the chain dynamics, the structural dynamics causes the coupling between these eigenstates, and that mediates transport. And now I want to discuss how we can probe this, how we can probe this, the effect of the vibrational dynamics on the electron dynamics in such a system. So in the last few years, we've tried very hard in these conjugated polymers to make systems that are as weakly disordered as possible. Because what we want for our applications, we want high mobility systems, and for that we need to reduce the energetic disorder in these systems. And a particular class of polymers where we've been very successful with this are kind of systems like this. So we call them donor-acceptor polymers. The name doesn't matter, but it's essentially quite a complicated repeat unit. So this unit is repeated along a long polymer chain, and it turns out that these systems, they actually are a bit like graphene nanoribbons. So they are disordered. So this is a molecular dynamic simulation of the chain conformations in the solid state. So you can see that they have this characteristic spaghetti-like conformation. They meander and are rather disordered. But what's interesting is that if you go along a single chain, essentially the chain remains essentially planar. What we don't have in these systems are basically torsional. So essentially, in a polymer chain like this, if you think about what potential disorder can you have, one source of disorder is, of course, torsions. If you have a single bond at this location here, you can distort the polymer chain, and you can have a kind of a torsional defect. And it turns out that these torsional defects are very detrimental. They cause a lot of the energetic disorder in these systems. So in systems like this, the polymer has been designed to minimize these torsional defects. And essentially in the solid state, we have this kind of graphene-like nanoribbon structure where, although the chain meanders, the torsional angles remain close to zero. So they remain planar. And as a result, these are actually surprisingly low disorder systems. If you measure the Urbach energy, Claude talked about the Urbach energy of indium gallium nitride. Systems like this actually probably have slightly lower Urbach energies than the indium gallium nitride that you talked about. So we get Urbach energies on the order of 23 millielectron volts in these systems, which is surprising given that it's structurally completely amorphous. So there is no X-ray diffraction. In X-ray, when we do X-ray diffraction, we see hardly any sharp diffractions. So structurally, this is a mess. But somehow locally, the local electronic structure is sufficiently well defined that we can achieve a low degree of energetic disorder in these systems. The transport signatures are very different to the molecular crystals. So if you measure, for example, the temperature dependence of the mobility, you typically see that as you cool down to low temperatures, the mobility plummets, the mobility is thermally activated. And that's because, in order to move through this disordered network of sites, you need to have thermal energy to get from site to site. And as low temperatures, that's harder to get, and as a result, the mobility reduces. We also see no Hall effect, so we try to measure the Hall effect, and in molecular crystals, it's a really beautiful Hall effect, but in these polymers, you don't. So that all suggests that static disorder and localization due to static disorder is much more important in these systems. In order to get a bit more quantitative information about these systems, I now maybe want, in the last couple of minutes, talk a little bit about an attempt to quantify some of the timescales involved in the hopping processes. And for that, we've used a technique that I don't want to discuss in more detail, but it's basically electron spin resonance. So electron spin resonance is a technique that's a bit like NMR, but it uses not nuclear spins, but electron spins. And essentially what you measure in ESR is the lifetime of spins. If you have a plyomagnetic field, there is a spin up and spin down level. They're not at the same energy because there's a Zeeman splitting between the spin up and the spin down state. And if you basically kick up an electron from the low energy spin down state into a spin up state, it will take a characteristic time, the spin relaxation time, for it to return into the spin down state. And so these spin relaxation processes are very interesting to measure because they give you some information about the charge dynamics. And the reason for that is that essentially spin relaxation happens by the electrons seeing time-dependent magnetic fields. So if you can do an ESR experiment by, for example, exciting spin up electrons into spin down electrons into spin up states by a microwave field that provides the energy, that Zeeman split energy from spin up to spin down to spin up. In a crystal, as the charges are moving, they do see time-dependent fields because they see local magnetic fields, for example, hyperfine fields due to nuclear magnetic moments. So as they move through the molecular lattice, they do see time-varying fields. So and that means that we can use measurements of spin relaxation to probe the charge dynamics. I hope that it's not important to understand this, but it's just to explain why we use this ORB technique to probe charge dynamics. And so what you can see on this plot is the temperature dependence of the spin relaxation time as a function of temperature. So I want you to focus on this bottom plot here. It's the so-called T2 spin relaxation time that's relevant here. So the spin relaxation time is long at very low temperatures. And that is because at very low temperatures, the charges are completely localized. They're just basically sitting in some low energy state where they remain forever. Yeah? And when they're sitting there, there's no time-varying fields. They just see whatever the local hyperfine field is there and happily process around that hyperfine field, and they don't relax their spin. And that's why the spin relaxation time at low temperatures is relatively long. As they then start moving, as you increase the temperature, the spin relaxation goes down because they hop. So let's say initially you have the charge sitting in this particular segment of the polymer chain. On that side, the charge sees a particular value of the local magnetic field due to these nuclear magnetic moments and processes around that, the local field. But when it moves onto the next side, the orientation of that local magnetic field due to the nuclear magnetic moment is different because these nuclear magnetic moments are not aligned. They point in a different direction on this side than on that one. And as after the charge hops, it processes around a different direction. So the hopping basically causes the precession axis to vary all the time, and that's a source of spin relaxation. So we can use the measurement of the spin relaxation time to basically quantify the hopping frequencies. The time scale over which spin relaxation occurs is directly giving us a measure of the time scale over which the charges hop. And you can, at about 50 Kelvin, there is a change in the temperature dependence, and the spin relaxation time increases again. And that is because the charges are now moving so fast that they don't have time to process. They spend little time on each side, and the time scale for precession is too slow. They have moved on to the next side before they have had chance to undergo one cycle of precession. So this is a regime called motional narrowing. So essentially the charges are then averaging over the local magnetic fields that they see. So in this regime here, then as they move faster and faster, spin relaxation becomes less and less effective. And so in this regime, we can actually extract hopping frequencies and hopping length. So the motion frequencies come directly from the spin relaxation time. So you can see that at very low temperatures, the motion frequencies are very slow, a microsecond or so. They spend microseconds on each side. And as then the temperature increases, the motion frequencies come up. At around 150 Kelvin, we have motion frequencies of a nanosecond. We measure at the same time the mobility, and then using this relationship here, the so-called Einstein relationship, we can then also calculate hopping distances. And at 150 Kelvin, we have hopping distances of about 20 nanometers. So we now know that these charges hop about 20 nanometers long every nanosecond. So every nanosecond, they find a site in which they spend the next nanosecond, and then they move another 20 nanometers. So that's useful if you are trying to understand the kind of transport in these systems. Having experimentally determined time scales and length scales is a useful quantity. I wanted to. How much time have I got left? Not much. But how much is not much?
Well, officially zero.
Zero. So what do I do now? Maybe just give me 1 minute. Because actually the interesting regime of spin relaxation is this high temperature regime where this motional narrowing seems to stop. What we would have expected is that at high temperatures, charges move faster and faster and faster, so the spin relaxation should have got less and less efficient. But actually, around 150 Kelvin, this stops, and the spin relaxation becomes more efficient again. And it turns out that this is very similar to what's observed in the molecular systems that I started out with, talked about in the beginning. If you measure the spin relaxation time of one of these molecular crystals, you get a very similar behavior. Around 150 Kelvin, the spin relaxation time has a maximum and then decreases towards room temperature. And that's surprising because the temperature dependence of the mobility in these two systems is very different. Here we have a thermally activated transport, and here it's a band-like temperature dependence of the mobility. So we think that this regime is actually allowing us to probe these. I don't have this time to discuss the details, but essentially in the small molecules and the polymers, you have a very similar coupling between the charge dynamic and the structural dynamics. In the small molecules, I explained that in this transient localization regime, you have a rapid oscillation of the carrier wave function that's driven by these molecular motions. And in the polymers, you actually have the same thing. The structural dynamics of the polymer chain also cause the electron wave function to shuttle back and forth along the polymer chain very rapidly. And we believe that in these molecular motions are driving spin relaxation. So the kind of similarity that we see in the spin relaxation time, we believe is caused by this close coupling between structural dynamics and charge dynamics, which actually on the local scale is very similar in the two types of systems. So with that, I thank you for your attention and thank Richard for giving me a little bit more time. Maybe the acknowledgements are not so important, but very happy to take your question if you are.